Hello, my name is Nicholas Lokentor, and my research topic was discovering how machine learning algorithms are implemented on the hardware level.
Taking a look at the agenda, I will first be starting with some brief background knowledge on machine learning and talking about the forms of algorithms that exist. From there, I'll begin transitioning into how the algorithms translate to a hardware level and how stochastic computing is currently being implemented to perform these algorithms. And I will end with results and conclusion and the future outlook on machine learning hardware. So, what exactly is machine learning? Well, machine learning is the process of using statistical analysis to discover patterns that are present in massive amounts of data. With different algorithms, predictions can be made for new input data after having undergone training on a given input set. Since there's so many types of different algorithms, it's not your typical one algorithm fits all. Rather, you need to test and train different models to see what works and what doesn't with a given data set. A recent buzzword in the world of machine learning is deep learning, which is an advanced form of machine learning, using many hidden layers that process an input layer to give the final result in an output layer. With all of these hidden layers, the computational methods use processing resources to make the predictions, but don't always use up all the resources available. This figure shows the hierarchy of machine learning, and you can see how it breaks down into three main learning types. The three main learning types are unsupervised learning, supervised learning, and reinforcement learning. Each main type consists of sub-algorithms that work in that style. For example, if you are looking to predict something in the future, such as weather forecasting or market forecasting, you would use regression, falling under supervised learning. If you want to do something such as have a robot navigate on its own, you'd implement reinforcement learning. Piggybacking off of the figure from the previous slide, the three main types of learning are supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is when a model is given a set of data made up of inputs and their correct output, and the model is trained on this to find a relationship and be able to take in a new input and accurately predict the correct output. Unsupervised training gives the model input data, but not the output data. Rather, the model is left to discover a pattern that relates amongst the input data. Reinforcement learning is similar to creating a robot and letting it learn how to walk on its own. First, you'll see it maybe fall over, bump into things, trip on its own legs, but eventually it'll start walking correctly. Reinforcement learning is, in a sense, similar to unsupervised learning, since there's no correct output label given to the data, but the model will learn over time by exploring its own environment. Some examples of algorithms that fall under supervised learning are the k-nearest neighbor, decision trees, linear regression, support vector machines, and neural networks. When you think of machine learning, you're probably thinking of an algorithm that falls in this category, as you give data to train the model with, and then you would give it new input data to accurately predict an output. Moving on, we have the unsupervised learning type, and some examples are the k-means clustering, which is pictured to the right, where if a input data falls under a cluster of other input datas, it'll probably be classified how those are, and another algorithm type being the association rules. Unsupervised learning is rarely used for prediction modeling, which may be unfamiliar to some. Examples of reinforcement learning are Q-learning, temporal difference, and deep adversarial networks. Since each model works very differently and would be applied for different data sets, it would take way too much time to discuss them all, but a simple Google search for an interesting model could return results quicker than me explaining them myself. I'm able to touch on neural networks briefly since I've become exposed to them in another course I'm currently taking. But the gist is that the input data is fed into an input layer made up of neurons, and each neuron performs its own transfer function that will calculate an output based off of its input. With that output, it will send it to each neuron in the next layer, so on and so forth. The connections between two neurons in between two layers has a weight assigned to it, which tells the receiving neuron just how much to favor the output result from the sending neuron. After however many layers there are created, the final layer is reached, known as the output layer, and the model will return a result. Now that a brief background on machine learning has been discussed and algorithms have been introduced, I'll now begin transitioning to the hardware side of things and seeing how these mathematical functions are implemented on a circuit level. Regardless of the model picked for a certain prediction or function to run, a large amount of computational resources will be used and needed for iterating through all of the data and discovering patterns amongst that data. During the training phases of models, they'll extract a classification for a given set of input data and map that classification to its correct output. After the model discovers the pattern existing in the data, it extracts features that are present in the input data and translates that to be used for predicting outputs from new input data. Here you can see an example type of architecture for the anomaly detection engine, also known as AID or ADE, where raw input data, whether it's an image, video, pattern, or voice, is fed into the architecture, and it will extract features present to be either used in making classifications, storing them, or transmitting them for use somewhere else. Looking at the diagram, you can see that the pixelated C is sent in as a raw data to the first layer, which is comprised of 4 nodes, which then comes narrowed down into 2 nodes, and then narrows down into the last layer in 1 node, known as the output layer. The most widely known model for machine learning, since it's been used as a buzzword when talking about artificial intelligence and whatnot, is a deep neural network model. An example of a deep neural network is seen here to the left, which is a deep belief network, and is made up of restricted Boltzmann machines, known as RBMs, and these RBMs are stacked on top of one another. RBMs use a gradient-based contrastive divergence algorithm, which utilizes a high amount of resources and large power consumption from the processors. This has led ASIC and FPGA researchers and designers to create their own processor suited solely for performing neural network calculations. By doing this, these designers and researchers are able to implement what they need and optimize it accordingly, reducing all waste. Since the main computation of deep belief networks involves over hundreds of matrix multiplications, which are then followed by nonlinear functions present in each layer, these networks can very quickly become costly in terms of power consumption and high silicon area, which has been found in VLSI implementations. The nonlinear functions also implement lookup tables, which require large amounts of memory, again, reinforcing the need for dedicated and optimized hardware in the world of machine learning. Besides power consumption and wasted resources, there are also other issues that become evident with how machine learning is performed on everyday hardware, most importantly being the scalability of it. Recent networks have begun to include hundreds of millions of multiplication functions, which will hurt performance times when running on the current unoptimized hardware, and is just currently unscalable with what we have. Now that the hardware issues have been talked about with the current architectures and everyday design for machine learning, I'll now move on to stochastic computing and how that seeks to solve the issue. Stochastic computing involves converting numbers or raw data into sequences of bits where each sequence does not depend on the value of the bit being high or low, but rather on a statistic of what the sequence means. The input data becomes represented as either unipolar or bipolar, where unipolar is having the bit be either a 1 or 0, while bipolar allows the bit to be -1, 0, or 1. The three main functions we'll look at with stochastic computing are multiplication, addition, and functions, which are implemented as finite state machines, although stochastic computing is able to perform all other arithmetic functions. For performing multiplication, stochastic computing uses either an AND or an XNOR gate, as seen by the figure on the right. For the AND gates, the output is simply just input A ANDed with input B, while the XNOR gate computes the product by taking the result of ANDing A and B and ORing it with the result of 1 minus A ANDed with 1 minus B. In terms of addition, stochastic computing uses either a 2 to 1 mux, assuming it's just adding two inputs, or an OR gate. The behavior for the mux is input A ANDed with S added to B ANDed with 1 minus S. The behavior for the OR gate consists of adding inputs A and B, and then subtracting A and B with the result from the sum. Although from the surface level in the last slide, addition seemed to work perfectly without any issues, there does exist a problem. The issue is that while performing addition, a precision issue arises with the usage of both gates, since the mux scales the input down for as many times there are inputs, which means for a 2-input mux, it'll scale it down twice, in conjunction with the OR gate also scaling down the inputs. Since this could lead to inaccurate results, an accumulative parallel counter was introduced which takes n parallel bits as inputs and adds them to the counter in each clock cycle. Now with a variance of the sum, the addition function now results in lower latency and converts the stochastic stream to binary form. Since many algorithms present in the world of machine learning use hyperbolic tangents and exponentials in their calculations, along with many other functions, these functions are represented as finite state machines in stochastic computing. Example finite state machines for calculating the hyperbolic tangent and exponentials are shown, with label A displaying the hyperbolic finite state machine representation and label B showing the exponential representation. Now that we've discussed the basics of stochastic computing and how the functions are implemented with the gate level logic, we'll now look to see how it's implemented on a circuit level. Shown here is the data flow for a neuron that has been implemented for stochastic computing. The data input can be seen as being fed into AND gates for multiplication, which their output is then fed into a mux for addition, whose output is finally ending up at the finite state machine where the activation function is present and will determine the output. From there, the output can be sent to another layer or the output layer. In further discussion about stochastic implementations for deep belief networks, the figure shown here on the right will be used as a foundation. Now, this figure does look similar to a deep neural network, since a deep belief network also has nodes in different layers connected to each other with different weight values. And inside each node, you can see the sigmoid symbol, representing that the activation function is nonlinear. In the output layer, you can see the symbol of a plus sign, showing that the activation function there is an addition function. This figure here on the right shows what each neuron would look like on a gate level schematic. The topmost input is the bias in the network, which is a predefined value, here being 1. The inputs are weights and results from either previous neurons in the layer before, or if it's raw input data. The weights enter a B2IS, which is a binary to integer stochastic converter, while the result value enters a binary to stochastic. The outputs of the AND gates are then added in a triadder, which then undergoes the hyperbolic tangent function to produce an output. Shown here on the left is a generalized design layout for an FPGA implementation of a processor that could be used strictly for machine learning computations. We can see that the input data is fed through logic, which is then stored in registers and then fed back to itself. This is similar to an input data being sent into a neural network's input layer where the nodes compute something, which would be the computational logic, and then they output them into another layer and then feed it back into another layer, going from the register back into the logic, back into the register, and so on and so forth. When it's finally at its last layer, the combinational logic will send its output to the output, similar to the output layer in a neural network. FPGAs allow us to do this since they're field programmable gate arrays for a specific purpose and are optimized to just what they need to do at a certain time with no other resources going to waste. Shown here on the right is a tensor processing unit, which will be referred to as a TPU. TPUs were developed by Google and are essentially specialized ASICs. Although Google owns this design privately, users are able to utilize them by using Google's cloud service in order to run their machine learning code on a computer made up of thousands of these TPUs in Google server rooms. Dating back to 2007, TPUs were designed to work with more input-output operations with large datasets while maintaining precision. Currently, Google is on their third generation of the TPU chip design, showing how mainstream machine learning is becoming. With big players in the field of machine learning now, like Google, we can only know how much money they will dump into optimizing and researching these designs, and shows that they're taking a big role on it as they expect neural networks to become a great part of their software and architecture. Here are some stat metrics for the tensor processing units showing how the cores are connected, the hardware behind them, their power consumption, performance, and even the software running on them. During this class, we have discussed a lot about performance and power consumption, and as seen by the TPU descriptions, we see that these processor chips are even faster than graphics cards while having their power optimized as much as it can be. Similar to the RISC-V architecture, TPUs operate in a pipeline, here being 4 as opposed to the 5 in RISC-V. The core description is fascinating as it shows that by forming quote-unquote TPU pods, training of models can be done in 30 minutes, whereas they used to take up to a whole entire day to compute. The image on the left shows a fully functioning tensor processing unit board that can be inserted into Google servers for usage at any moment. These boards look similar to our microcontroller boards that we've used in previous classes, but have become optimized solely for usage in machine learning computations. On the right, you can see the architecture that makes up the die, which has components that we discussed previously, such as the activation and the matrix multiplication units. Connected through PCIe interfaces, the TPU is able to use all bandwidth available for reporting results back to the host and has access to the DDR3 interfaces for memory usage. As both of these components become quicker with each generation, being DDR4 onto DDR5, and the recent advances in PCIe Gen 4, the transfer speeds will only increase and make these processing units able to report quicker. After exploring how stochastic computing can be implemented on the hardware level and looking at other implementations for machine learning algorithms, I'll now discuss the results on how specific implementations compare against the current everyday architecture that we've currently been running machine learning algorithms on. Presented here are the hyperbolic tangent function results that has been run on pre-implemented stochastic computing devices versus a post-implementation shown on the right. Looking at both graphs, you can see that the left one staggers to reach its output of 1, taking about up to 2 seconds for all the functions to hit it, while the right graph shows that after about 0.75 seconds or so, all the functions have reached their output. This is because the stochastic implementation has proven to reduce the runtime while keeping efficiency up and using all resources that it has available instead of wasting them. Similar to the slide previously, this is demonstrating the exponential results as opposed to the previous hyperbolic tangent. On the left again, we have the pre-implementation device, and on the right, we have the post-implementation. Looking at the two, we can see that on the left, it takes maybe about 4 seconds for all the outputs to reach zero, while on the right, you can see that after 2 seconds, all the functions have reached their output of 2. Again, reinforcing that if you're using hardware optimized for a specific purpose, you will achieve better results than unoptimized hardware that wasn't really made for specific functions and computations. So, what did we learn? We learned that creating specific chips for a specific purpose removes any extra and unnecessary resources that weren't going to be used effectively, and have even created an entirely new product that will be essential in the coming years as machine learning grows more and more. The tensor processing units discussed along with stochastic implementations have proven to decrease the runtime for these machine learning algorithms and will pay off greatly as input datasets become larger. Keeping the runtime performance as low as possible is one of the most important factors needed in machine learning, as nobody wants to wait days for their models to train. Speaking from personal experience, I had to leave my laptop running all night long training a support vector machine just to wake up and see that it's still not completed. Machine learners around the world will greatly benefit from these new hardware implementations, as optimizing for machine learning is a top priority and new ways are constantly being discovered. Listed here are the references that I've used to compile the information that I presented today. Included are links for images and general information that I discovered along the way. Here are the rest of the resources and references that I used. I hope you enjoyed the presentation and learned something out of it. Thank you for listening.